Researchers in China have used a procedure described as chemical surgery to mend harmful mutations in human embryos for the first time. The scientists found that it was possible to repair a faulty gene that gives rise to a serious blood disorder called beta thalassemia, which can be caused by one misspelling in the DNA code. None of the embryos treated in the experiments were used to produce babies, and doing so would be illegal in the UK and many other countries. But the work proves that the method, known in genetics as base editing, could be an effective way to prevent inherited diseases. Base editing was dubbed chemical surgery by its inventor, David Liu at Harvard University. In the past decade, scientists have developed a range of powerful tools to edit the genetic code, the most popular of which is called CRISPR-Cas9. The method uses enzymes to make precision cuts in faulty genes which the body can then repair with the correct DNA. CRISPR, or to give it its full name, CRISPR-Cas9, allows scientists to precisely target and edit pieces of the genome. CRISPR is a guide molecule made of RNA that allows a specific site of interest on the DNA double helix to be targeted. The RNA molecule is attached to Cas9, a bacterial enzyme that works as a pair of molecular scissors to cut the DNA at the exact point required. This allows scientists to cut, paste and delete single letters of genetic code. Thank you for your feedback. In 2015, scientists led by Zhengzhu Huang at Sun Yat-sen University in Guangzhou, China, tried to use CRISPR to correct abnormal beta thalassemia genes in human embryos without much success. In the latest breakthrough, the same team turned to base editing instead. To perform the experiments, Wang first created a batch of cloned embryos. His team took skin cells from patients with beta thalassemia, removed their DNA-containing nuclei, and dropped them into donor eggs that had their own nuclei removed. The eggs then developed into early-stage embryos that carried the beta thalassemia mutation. Base editing uses similar enzymes to CRISPR, but instead of cutting right through the double strand of the DNA helix, the enzymes instead change single letters, or bases, of the G, T, and C that make up the genetic code. For many patients with beta thalassemia, the disease is caused by a mutation that switches an A for a G writing in the germinal protein and cell. The researchers show that the new procedure worked to some extent. Humans carry 2 copies, or alleles, of every gene, and in many cases both versions have to be healthy to avoid disease. In the study, base editing sometimes repaired only one faulty gene rather than both, creating so-called mosaic embryos that had both normal and mutant cells. This looks very promising, but all the embryos from which they were able to get information from more than one cell were clearly mosaic, with some cells still carrying both mutant alleles, said Robin Lovelbadge at the Francis Crick Institute in London. The Chinese team has not suggested that the procedure is ready to use in humans, especially as they found that it sometimes created mutations instead of fixing them. But researchers do see a role of gene editing in preventing heritable diseases from being passed on. For many years, we have been saying that direct gene editing in embryos is some way into the future. Now the future is here and there is much to consider, said Darren Griffin, a geneticist at the University of Kent. The paper itself represents a significant technical advance because, rather than using the classic CRISPR technology previously reported, the current base editor technology is an adaptation that chemically alters the DNA bases themselves. While this is undoubtedly a highly significant advance, it is important not to get carried away about its widespread utility if put into clinical practice. An embryo would still need to be diagnosed as abnormal, then the base editor applied, then re-diagnosed to make sure that it had worked. This would be an involved procedure that would be very expensive. In the meantime, the ethical implications of gene manipulation in embryos need a thorough examination, where safety is of paramount concern.